Take a moment to read through the question completely, identify the values that were given, and try to visualize what's going on in this problem. We have an archer who's on a parapet, so up at the top of a castle wall that is 55 feet above the ground. He can shoot an arrow with an initial speed of 110 feet per second, and we want to know what is the range of his bow. From this height, the arrow should have a launch angle of approximately 40 degrees to achieve maximum distance. We saw that the maximum distance is 45 degrees when you're going from ground level to ground level, but if you're firing from a height or firing up onto a platform from below, that changes that maximum or minimum angle somewhat. So the first thing that we should do when we have any problem is to, number one, draw a picture and try to understand what's going on here. So we have an archer who's on a parapet up on top of a wall. This archer up in the parapet is going to fire his bow. We're told at an initial angle of about 40 degrees and with an initial speed of 110 meters per second. I drew my archer too close to the top. This archer is going to fire his arrow at 110 feet per second at an angle of about 40 degrees, and we can imagine that this arrow is then going to arc through the air, and it's going to fly and it's going to land over here somewhere. And what we want to find is what is the range, and what we'd understand in this case, the range would be how far is the arrow going to fly horizontally from the castle wall where it's launched to where it lands, right? We were looking for the range, how far it's going to go. In this case, we're told the launch speed of the arrow, which we know. We also are told that this archer is up on top of the wall, 55 feet above the ground. And so if we're trying to solve a problem like this, if we're trying to plan our solution, we would see that the arrow is flying through the air. After it's launched, it's not touching anything, it's just flying through the air, and that's projectile motion. Nothing is affecting its motion other than gravity, giving it this arced trajectory, and so that's projectile motion. And so we can solve this as a projectile motion problem, where projectile motion is split up into two parts. We have a x direction, where we have uniform motion. There's nothing affecting the motion of the object in the x direction, nothing speeding up or slowing down, so it's just going to have uniform motion, constant velocity motion horizontally in the x direction. In the y direction, we have gravity acting on us, because gravity is acting even though the object is not in contact with the earth, and so we're going to have constant acceleration equations to solve in the y direction. So in this situation, for us to execute the solution, what we're going to do is to lay out all the variables. We know what variables we need for uniform motion. We know what variables we need for constant acceleration, and we'll lay out what we have, what we're trying to find, and then we'll be able to plug these things into equations and actually solve them. So in this context of uniform motion in the x direction and constant acceleration motion in the y direction, we can look at the values we've been given and try to figure out what we know, what we're looking for. So the arrow is fired from the top of the castle wall. The arrow is going to go up and come back down. So the arrow starts out 55 feet above the ground. It's going to end up down at ground level. So the entire displacement, vertical displacement of the arrow as it moves is going to be 55 feet, but it's going to be 55 feet downwards because it ends up below where it began. As it's flying through the air, it's also moving horizontally. It's moving this horizontal distance, and we recognize this horizontal distance is the range that we're looking for. That is going to be our displacement in the x direction, which we'll just call r, so that we have a separate variable, something to call it, and then we'll be able to solve algebraically for that quantity. This is a projectile motion problem, which is free fall in the y direction. So although we're not given it explicitly, we can say implicitly that the acceleration due to gravity is, the acceleration in the y direction is the acceleration due to gravity. You notice here how I'm already making the mistake of jumping straight to 9.8, which is typically the value we use in the metric system, but notice here everything is given in feet, and so I have to use the value in feet per second, 32.2 feet per second. Also, gravity is pulling downwards, so the acceleration should be negative. In this case, we're told that the bow is fired with an initial speed of 110 feet per second, but it's fired at a 40-degree angle. So this is the initial speed, we're told right there. But that initial speed of 110 feet per second is at a 40-degree angle. And so that's not the X direction or the Y direction. That's at some other angle between the two. And so what we have to do is draw a vertical line through the tip, a horizontal line through the tail, and we need to break this one vector up into components in the X and Y direction. There's going to be, this would be the overall V initial vector. We're going to break that up into an initial velocity in the Y direction and an initial velocity in the X direction. But since there's no acceleration in the X direction, I just call that Vx because it's the initial velocity in the X direction, but it's the only velocity in the X direction. The magnitude of the vector is always the hypotenuse. When I use this vertical line through the tip, horizontal line through the tail, that gives me the X component is adjacent to that 40-degree angle, so I'll use cosine. The Y component here is opposite that angle, so I'll use sine, and I'll use trigonometry to find the X and Y components of that initial velocity vector. So I calculate my values here. Notice that I have used several more decimal places than I need. Again, I'm going to round everything at the end, but I want things to be as correct as they can be at the moment. I also want to check the directions, because these sines and cosines are just going to give me positive values, but the X direction is going to the right, the Y direction is going up. Those are both the positive directions. So these values are both correct in that regard as well. So the initial velocity in the Y direction can go into my variables in the Y direction, and my X component of the initial velocity can become my velocity in the X direction. So now I want to find the range. The range is in the X direction. To find the range, I need to know the other two variables. I have one of them for my initial velocity. I don't have time, but when we're looking at projectile motion, we have time in the X direction and we have time in the Y direction, and those two times are going to be the same, because while we consider the time that the projectile is moving horizontally as it goes from its starting to ending point, the time that the projectile is traveling vertically as it goes from its starting to ending point in the Y direction, that's the same time, because we're looking at two different dimensions separately, but really it's one projectile, it's in one flight, it's moving horizontally the same time that it's moving vertically, because it's really following just one trajectory. So we have the same time here. If I can find the time here, I can find the time here. If I can find the time here, I have everything I need to find that range. I can look over here. This is the Y direction with constant acceleration. I have three variables, and so I can use those to find the time. The first thing I'm going to do is to write out the relevant equation. I don't know my final velocity in the Y direction, so I'll pick the constant acceleration equation that doesn't have Vf in it. Start by writing out the equation and then plug in variables. Notice that this is a quadratic equation. I've got a t squared term, a t term, and a constant term. So I want to put that in standard form. I set the whole thing equal to 0, and I put my t squared term, my linear term, and my constant term, so that this will be my A, this will be my B, and this will be my C when I plug into the quadratic formula. This is a quadratic equation, so I should get two solutions, but I know that I'm measuring delta t, that's a time increment. Time has to go forward, so I should keep my positive value. I can discard the negative value as not being physically reasonable. So I found delta t. I'm looking in the Y direction, so this is my delta t in the Y direction. But we said that the time in the Y direction is also the time in the X direction, so I know that value as well. Now I know two values in the X direction. I can use the third one to find my displacement in the Y direction. So now I'll use the equation in the X direction. In the X direction, I have uniform motion, and there's only one equation for uniform motion. I start by writing out the equation. Now I'm going to plug in the values. So I can solve for r here. R was our displacement in the X direction. I get 426.89. That should be feet, because we're measuring everything in American units, and the range is a horizontal distance. I kept a lot of sig figs, and now I'll go back and I'll say I had 2 sig figs there. I had either 2 or 3 sig figs there. So in this case, I might just err on the side of caution and call this 427 feet. We'll call that 3 sig figs. And that is how far away from the castle wall we would expect this archer to be able to reach with his arrow.